Thanks for joining us. I'm Anthony Reid from the Geological Survey. Today we've got a really special interview. We have Professor Richard Ernst. Richard is a world-renowned expert in large igneous provinces in all aspects of their geology. He's literally written the book on the subject. He's from Carleton University and Tomsk State University in Russia. And I'm joined here with Lucy McGee from University of Adelaide. Thanks for joining me, Lucy.
No, thanks for having me. I'm excited.
Definitely, really looking forward to this chat with Richard. We'll start with the very basic questions. How large are large igneous provinces? Can you have medium large igneous provinces? What is the sort of scale of these magmatic systems?
Yeah, thanks for inviting me. This is really cool. And we're happily done with winter here, so it is cool. It is nice to be warming up here.
Excellent.
So yeah, large igneous provinces, which is sort of a passion of mine. These have, we have the minimum size, which was sort of set up when Mike Coffin and Ola Veldholm just sort of first characterized them back in the early 90s. And since that point, it's really remained this idea that these were a minimum of 100,000 cubic kilometer events. There was tend to be a notion of them as we came along to be short duration and then interplate. So in terms of those are the three characteristics. And in terms of size, the minimum size I mentioned, but they can potentially get up to an astounding nearly 80 million cubic kilometers.
Wow.
Oh, yeah.
Right? And one of the ways I've sort of talked about these is the minimum size would cover the entirety of Canada or the U.S. or to thicknesses of 4 or 5 meters, the entire country, right?
Oh, wow.
For the largest events, things that would cover the entire country up to about 8 kilometers. So yeah, these are astounding events. And
that is a huge amount of magma to come out of it.
And whether there's any kind of natural cutoff to things that are much smaller, it seems true because these do seem to be particularly large features. The best studied ones, the younger ones that are well preserved, seem to have a minimum volume of about 200,000. So in some ways, the natural cutoff might be around 200,000 cubic kilometers. Right. So 100,000 seems safe as a cutoff before getting to much smaller interplate events.
Oh, wow, that's a really great way of visualizing it, imagining it sort of covering a whole
continent,
landmass like that, isn't it? It's amazing. So you mentioned about them being sort of reasonably short duration. When we're thinking about maybe single volcanic eruptions like a stratovolcano or something, sometimes we think of those processes as being, or those processes are modeled on the scale of maybe days to decades. What kind of timescales are we thinking about here?
Yeah, that's one of the really hot areas in recent times is sorting out the time scale, time duration. Earlier with less precise dating, it was unknown whether they were tens of millions of years or longer. But the really super high precision uranium-lead dating to the precision of about 50,000 year precision is telling us that there are a lot of these events that are due, most of it in less than 1 million years.
Wow.
So this huge volume, the Siberian Trap event, the Deccan event of India, the on and on, incredibly short durations for many of them about 1 million years or less, including, for instance, the potentially the largest of them all, or largest continental one of them all, the Central Atlantic Magmatic Province, which covers some 10 million square kilometers covering adjacent parts of the Atlantic Ocean. That also seems to have been in place, at least all the precise dates from a variety of places within 1 million years. There's some events, though, that are multi-pulsed and are up to tens of billions of years long. So, so yes, incredibly short. And in some cases, multiple pulses that might last tens of millions of years or be spaced over tens of millions of years.
Okay. And so have these large igneous provinces occurred throughout Earth history? Are they something which happens periodically, or is this only found in the recent times and we never see it in the Proterozoic and there's lots in the Archean? Or is this some sort of cyclic, is there a cyclicity to any of these events?
First part of the question is, they are really present throughout time. Right. In the original configuration, the original recognition of them, Mike Coffin took this record of continental flood basalts that was a lot in the literature at the time and paired it with these oceanic plateaus, which were essentially the oceanic equivalent. And then that took it back, a few 100 million years or so. Then it was realized that these massive, huge dike swarms, dolerite dike swarm events, that could cover, where swarms could have a radius of over 2,000 kilometers away from the center. Those are the continuation of the record back through the Proterozoic. And then in the Archean, a number of these Archean greenstone belts, particularly those with significant komatiitic sequences, kind of point to a sort of an interplate origin, and those two we think of as large igneous provinces. So throughout time, in terms of periodicity, that's a bit of an open question. When you do stuff like wavelet analysis, another kind of statistical analysis of lip occurrence through time, you do get some cyclicities for parts of the time. In the youngest record, you do see a sort of 30 million year-ish, 30 to 20 million year-ish kind of cyclicity. And then over larger periods, you have a sort of a wavelet analysis suggesting a 500 to 700 million year cyclicity. So that's sort of a supercontinent cyclicity.
Scale. Is there a spatial association with any of that periodicity?
Not that we know, because one of the big problems is as we go back through time, we're still sorting out
where everything was.
Where was everything at that time? Good questions.
And also one of the other things that we don't know really well is the record of oceanic lips back through time.
Of course.
So we know for the last, couple hundred million years, the existing oceanic plateaus, but as the oceans prior to that, are very poorly preserved.
They're consumed.
We only see that record, consumed. The plates are consumed. Oceanic plates consumed, then that record has to be in orogenic belts as kind of mashed up ophiolites. So it's, but we think if you take this combined oceanic and continental record, lip record, and extrapolate back the oceanic record at the same rate, these things are happening probably closer to every maybe 15 to 20 million years.
Right.
So fortunately, we're not in the middle of one right now, but they happen fairly frequently through Earth history. And just one other thing is that there have been a number of times when people have talked about, there's particular gaps in the record. There's very little in this, immediately Paleoproterozoic time in the sort of period there. Well, the gaps have been filling in. And as we've been discovering more events, there are very few significant gaps. I think the largest gap we have now is maybe 60 million years in the
entire Earth
record.
History.
Back into the Archean, then of course we have serious gaps, but that's and how far we go back. They may go back probably to at least 3 billion anyway.
That's pretty constant, really, isn't it? When you think about it, and each one maybe lasting around 1 million years. It's
a lot.
Yeah, that's a lot of activity. It's and thinking about other sort of knock-on effects of these huge outpourings. You've done a lot of work with other effects, including sort of climate change. Is that something that we see with every lip, or just the very large ones?
Yeah, that's one of the most exciting developments, right? Is the link with climatic effects, because with the really improved resolution of dating, then we're able to really match it to the sedimentary time scale and the geological time scale boundaries. Say yes, it's linked, or no, it isn't. And so many of these major events are right on top of the major extinction events. For instance, the Siberian Trap event, absolutely associated with the Permo-Triassic extinction. The Central Atlantic Magmatic Province, exactly on the Triassic-Jurassic boundary and its associated changes. The Deccan event, at 66 million years, right on top of the end Cretaceous extinction, although that one also has the associated meteorite impact. But you have these major correlations with major extinction boundaries. The smaller, there are a lot of ellipses that at this point we don't know what their environmental effect is. But a lot of them, obviously, they're not all mass extinction events. And so one of the frontiers is trying to figure out, okay, what are the specifics of each event? Are they happening during a time of where the climate's near a tipping point? then the pulse of a lip will push you right over.
Push it
it's
over,
a
yep.
very stable time, probably not. And the oceanic lips, which tend to be much larger in some cases, they have a reduced effect probably because of the buffering of seawater and the CO2 flux for them, has difficulty getting into the atmosphere.
So the main impact for climate change regarding lips is actually the CO2?
That's a pretty significant driver, yeah.
Right.
But it's a couple interesting things. You have a lot of lips that are associated with global warming periods, periods of what you might call hothouse times.
Yeah.
But paradoxically, there's some specific lips that are associated with snowball Earth when the climate went cold, and those are like one of the most significant glaciations, the Sturtian glaciation, one of these snowball Earth glaciations starting around 715 million years ago. That's exactly the time of some major large igneous provinces, the Franklin event of Canada and other equivalent in other blocks. Whether that's because of the sulfur pulse from this, whether it has higher sulfur pulse, that's one mechanism. And the other is this erosion. One of the things
physiological changes physiographic changes in the continental record.
Well, if you weather a large igneous province, basalt weathering is very efficient at sucking CO2 out of the atmosphere.
I see.
Yes. So for a equatorial, a non-polar, an equatorial located large igneous province, the weathering is much greater, and it can suck out the CO2 from weathering.
So it can go either way.
It can. Most of it goes warmer, and CO2 is certainly a control, but there's also we know there's mercury poisoning associated with many of these events, because one of the things you look for in the sedimentary record is some spikes of elevated mercury over total organic carbon, and that's a clue that there's a volcanism story going on.
Excellent. Richard, so we've talked about the timescales and the sort of size of these events. So what is the driver? What is causing all this magma? What is causing these large igneous provinces?
Yeah, obviously there's a lot of debate on that, right? My preference is that my view on this is that it's mostly mantle plumes coming from the deep mantle.
Yeah.
I'm persuaded by the idea of these giant radiating dike swarms that are associated with it, where the dikes converge on what we think would be the mantle plume center. And these are dike swarms that head out to 1,000 kilometers, 2,000 kilometers sometimes. And that's sort of consistent with a significant magma driver at the focus. We also have evidence in some swarms for magma moving sideways in the dikes, laterally away from the plume center region. So it really looks like in those cases, which I think is a lot of cases, all the action is within 400 or 500 kilometers of the plume center. And so mantle plume. There's other stories, there's other effects that are important. Once you have, if you have a plume there with elevated mantle temperatures, and then you develop a rift, then you get the White and Mackenzie sort of classic, partial melting from decompression. And there are other models that have been proposed. There's a lot of other models. There's that are related to, say, sort of back arc processes potentially, and juice. A lot of water gets down into the mid-mantle region. So as plumes are coming through,
that accentuates the melting.
Without plumes, you can get some juiced up magma that melts more easily. But from my perspective, the size of these events really calls for something like mantle plumes, and it's consistent with the idea that Earth has plate tectonics, which is a major driver. But there's a second kind of system, which is the plume system. And we have confidence that that's a global driver, a global process from what we see on Earth, but also from this planetary angle, if I might get in for a moment. And then when you look at Mars and Venus, there's no plate tectonics, but there's massive volcanism, and that's all plume-related volcanism. So
heat transfer from the deep.
Absolutely. Yeah. Wow, that's amazing. Yeah. So once you've just started up these systems with a plume, some huge heat-driven event, how do they stop? And can they maybe stop and start a little bit, or have rejuvenated volcanism at some time later? Do you see that at all in the record?
Oh, those are great questions. we think that we usually see a kind of a major initial pulse. And so what you need is some mechanism to take, mantle that has elevated temperature, maybe elevated volatile levels, rapidly to a shallow enough level to rapidly melt, right? And so under that, and so the plume comes up to the base of the lithosphere and spreads out. And so that's a very rapid process for bringing mantle that's available to melt, has elevated temperature and elevated volatiles to a level where partial melting happens really rapidly. So it
has to happen rapidly.
Pulse.
Yeah.
Once you have some rifting, that can give you a second pulse. And maybe there's kind of different configurations that might even give you a third pulse in some kind. The plume head continues, or the plume material still probably continues to rise up the plume stalk in most cases. There's continued flux, but it's a much lower level. We see that in the classic ocean island chains that represent, continued flux that, as the oceanic plate is moving across it, you get a line of volcanoes, and we see that rarely in the continents, but we see some examples potentially of a similar sort of plume tail process expressed in some continental areas.
Excellent. So that makes me think a little bit more about how the composition of these large igneous provinces might change between provinces, depends on the type of mantle you're melting or the crust that's interacting with it. So I guess the change in composition will also result in changes in fluid chemistry or I guess volatile chemistry of those rocks as well, which is something which is probably quite important for ore deposits.
The connection with the ore deposit angle is obviously important, hugely important. And here a thank you to industry consortium that has become interested in lips over the last 10 years or so, more interested in lips and funding of kind of basic work on large igneous provinces. So and that kind of reflects the recognition that things like the Norilsk, which has been long known that Norilsk in Siberia is such a rich nickel copper PGE deposit. It's part of the Siberian trap event. There are many other Siberian there are several other similar scale events even in Siberia of older age. And so it's led to a lot of thinking about, could any of these have an associated Norilsk? In the search for another Norilsk, what do you look for in a large igneous province? Are there geochemical things that tell you about some prospectivity? And that's an exciting area. I mentioned a paper that Julian Pearson co-authors, a pleasure of co-authoring as well, is it just came out in Lithos, and it provides a new diagram that is a lip printing diagram that starts to give us a way to just look at different lips, see their individual fingerprints, and potentially start to say, this one has potential for nickel copper PGs. Maybe this one has less potential.
Oh, that sounds amazing. Really useful.
But the other part of it is also trying to understand the plumbing system. So in one lip, you may have one chemistry that's good, another chemistry that's not very useful. And so you need to be able to try to find ways to track magma batches through the plumbing system to try and, vector towards, the prospective ones.
Yep.
Yeah, I was going to ask that because these things are huge, and, where is potentially going to be prospective and what's that going to be dependent on? But as you say, looking at the magma source and how, how much potential it has, it must be quite a tricky thing to track down.
Yeah, but it's tractable because we're understanding the plumbing system. We know that most of the action's probably within 500 kilometers or several hundred kilometers of the plume center. We also, kind of work that Graham Begg and others have talked about regarding, translithospheric zones and those being good, and maybe the combination of such translithospheric zones and proximity to the plume center is kind of a sweet spot. We're understanding that we have maybe there's an important magmatic underplate, crustal magmatic underplate that's part of the central region of many large igneous provinces. That may be spawning secondary intrusions that get into the mid crust and the upper crust, and at least with respect to, say, the Mackenzie large igneous province of Canada, the muskox intrusion, which had been long prospected, is linked to one of these these intrusions that's coming off potentially the periphery of a magmatic underplate. So that's a kind of another aspect. And, and on and on. And if I may just throw in this idea also of, we're not just looking for the magmatic ore deposits, we're also looking for
sure.
The idea that these are massive heat engines. And so they can pump a lot of heat, cause, groundwater circulation, enhance it, that leads to concentration of metals as well. And there are lots of examples of that as well. And they also, the sort of dynamics of above a mantle plume, also to control the location of sedimentary basins and their evolution through time. So it is part of a holistic kind of look. And I think we're just, we're beginning to...
Yeah, so I guess sedimentary basins, lots of basalts around. I just hear
That's
sedimentary
another
copper.
aspect.
I just think that's related. Sounds really interesting.
Oh.
Before we leave you, Richard, please tell us a bit more about Venus.
Yes, definitely.
What's
thank you.
what's the thing? What's the thing about Venus that has really, sparked your interest in this?
Yeah. Well, Venus is similar to Earth in many ways, size, internal structure, but it has no plate tectonics. It has a surface temperature now of 450 degrees Celsius, the temperature of a self-cleaning oven. CO2,
the green facies on the surface. That's it.
That's right. Huge content of CO2, 96%, 90 bar atmosphere. But my recent modeling has suggested Venus was Earth-like in its earlier history. And the great climate change on Venus is presumably linked to volcanism, large igneous provinces after large igneous provinces. And we're investigating a kind of a mechanism for multiple lips happening at the same time and potentially causing a runaway greenhouse effect.
Like a catastrophic.
And boiling off the oceans, etc. So that kind of aspect's neat. But the other part is, these are large igneous provinces, and in the younger record, no erosion. And so we can see areas where we can see, okay, this lava flow, we can map out its entire extent, and we can see the location of the magma chamber from which it came as a small depression. And so we can potentially scale the size of the lava flow, the size of the chamber, and potentially compute an R factor and say, whoa, which is of course important to the nickel copper PGE folks. And so we could say, this kind of intrusion on this location with respect to the, say, plume center, these have high R values. And maybe we can and maybe we can translate that to a terrestrial context and give us some predictive value on, with respect to a large igneous province system, which portions close to the chamber, the center, further away, or along a rift, what's going to give us higher R values.
So you've got a planetary scale analog model going there.
Exactly. Yeah, no, that's super exciting.
And how amazing to be using a planetary example as an analog for things happening on Earth rather than the other way around, which is, what we think.
I would expect as well.
Yeah, that's amazing.
Amazing work.
Yeah.
Fantastic.
Yeah.
Well, thank you very much for joining us, Richard. It's been an absolute pleasure. Really learned so much about Large Igneous Provinces. I think, we're really lucky to have your time. Thanks very much.
Thank you.
Thank you so much. I love the opportunity, and thanks so much.